I want to use the charts here to describe chemical properties. So let's pick a acid as an example. Actually, go edge here. Let's look at HF. That's the acid. Thanks. Okay. This is not working. Okay, there it is. So if we look at the chemical properties of HF, what would you say? Well, it's hydrofluoric acid. And so one of the chemical properties is it's an acid, right? So one, it's an acid. What do acids do? Acids react with bases. And typically what we think of is an acid is a proton donor, and a base is a proton acceptor. But will it react with all bases? What do you think? Hydrofluoric acid, does that react with all bases? And so if we want to be more specific, what bases, in other words, the question is, what bases or which bases will HF react with? And it turns out that this is a pretty easy question to answer if we use this chart method. And the chart method we're going to use is this zigzag pattern. I call it a zigzag pattern, but it's not officially named that. And so if I go back to the acid-base chart and I think HF, what bases will it react with? And so over on the left side here we have our acids. Over on the right side here we have our bases. And so if I think, this is on Canvas. Yeah. This is also in your manual. but it's a more descriptive chart. I don't know what happened to my, let me look for my manual. I could show it to you. So it would be under the supplement section, acids and bases. Acid base is 1 here near the middle. So we could use this chart. All I did was I just chopped out the center part for my chart here, but it's exactly the same chart. I think. This one, yeah, exactly the same. So we're looking at HF here. And we're looking at what bases it will react with. And so the acids are on the left, the bases are on the right, and then we ask ourselves questions like, for example, will HF react with the base chloride ion? And so if I look at chloride, it's here. Will HF react with this base, chloride? Yes or no? It turns out no, it doesn't. Will HF react with nitride ion?
Yes.
It turns out no.
It's because they're both weak.
No, they're all, like bicarbonate's weak. Will HF react with bicarbonate? Yes. How could I tell these? How I could tell these things is the zigzag pattern, right? So there are two ways of understanding this zigzag pattern. One way is this. One way is there going to be a driving force? If HF reacts with fluoride, what forms? If HF and fluoride react, we form fluoride and HF. Nothing changes, because if we donate the hydrogen to fluoride, then we're going to have HF, and then this is going to be left as fluoride because we're donating an H+. And so we get no reaction. I mean, we start off with HF and fluoride, we end up with HF and fluoride. There's no change. So there's no reaction. So what we need is we need a base that's stronger than fluoride. What are the bases that are stronger than fluoride? The ones that are lower than fluoride here, because we're on the right side of the chart. Strength increases as we go down. On the left side of the chart, strength increases as we go up. And so the strongest acid is on the top left here, and the strongest base is on the bottom right. So we need a base that's stronger than fluoride. So when I ask you, will HF react with nitride? No. Will HF react with H2PO4 minus? No. Will HF react with sulfate? No. Why? Because those are all weaker than fluoride. We need a base that's stronger. So HF will react with any base that's stronger than fluoride. And so if I ask what bases will HF react with, the answer is simple. Any base that's stronger than fluoride.
So the one that's right next to it, I noticed, they just cancel each other out. They don't go anywhere.
Yeah, right. It just cancels each other out, exactly. It's not going to go anywhere. It's just going in a circle is basically it. And so any base that's stronger than fluoride. And so we see that any base stronger than fluoride. A base that's weaker is not going to be favorable. There's going to be no driving force. So we're going to get a driving force with a base that's stronger than fluoride. And so this is where the zigzag pattern comes in. Since I can't edit on Adobe for some reason. I'm going to do it back here in Edge. So let's pick a base. Like I said, bicarbonate. And so if we go with bicarbonate, then this is the zigzag pattern here. We have HF reacting with bicarbonate. Okay, what forms? Okay, so this is step one. HF reacts with bicarbonate. And then what's going to form from this reaction, the products are going to be fluoride and CO2 and water or carbonic acid. So what we end up with as products are fluoride. So HF donates its proton to bicarbonate. Bicarbonate accepts the proton to make carbonic acid. Carbonic acid in turn decomposes into CO2 and water. And so the products here are going to be CO2 and water and fluoride. Okay, so what we do is we look for driving force. Now the driving force is going from a stronger acid, HF. It's still a weak acid, but it's stronger weak acid than CO2 and water. And so this would be the weaker acid. So we're going from stronger acid to weaker acid. Likewise, we start off with bicarbonate as our base here. And then we end up with fluoride as our base. So this is an inverted chart on the right side. So we're actually going from a stronger base here to a weaker base here. And so this is the zigzag part of the zigzag pattern here. On the other hand, if we tried to do a reaction with, let's say, HF and sulfate, let's go with that. If we tried to do the reaction with HF and sulfate, what would we form? So this would be 1, and what would we form? I'm sorry? Yes, so name those species. We'd form, what's this called? Bisulfate. Is bisulfate a weaker or stronger acid? It's a stronger acid. So what we're doing here in this case is we're going from a weaker acid, HF, to a stronger acid, HSO4 minus. Is that favorable? No. We expect NR here. Here we have driving force. Likewise, let's look at what happens with the base. We go from HF to fluoride. And so we're going from sulfate to fluoride. Going from sulfate to fluoride, what's happening here?
It's a weak base to a stronger base?
Yeah. We're going from a weaker base to a stronger base. So this is the zigzag pattern. We want to zig down, and then it's favorable. If we zig up, it's unfavorable. Do you see that?
So like a reverse C.
Mm-hmm. Yeah. Okay, so let's take a look at something else. Let's look at ammonium, for example. Ammonium's an acid. What does this acid react with? In an acid-base reaction, not everything. So, for example, will ammonium react with fluoride? No. So how would you frame this so that you cover all? species. If somebody asks you what does ammonium react with, what would you say? Would you list them one by one, or would you come up with just a general statement?
Cyanide and anything stronger?
No, there could be something. This table's not comprehensive. There could be something between ammonia and cyanide. If this were comprehensive, then you would be correct. If there's nothing in between, but there is something in between ammonia and cyanide.
Is there anything that's a stronger base than ammonia?
Yeah. What you'd say is it would react with any base stronger than ammonia. So as we go down here, then, like for example, dihydrogen borate. However, if we go up here, then it's going from weaker to stronger. So we need to go from stronger to weaker, downhill. It's got to be downhill. Does that seem pretty straightforward?
Yeah.
No? Yes? And so ammonium reacts with any base stronger than ammonia, which is cyanide, dihydrogen borate, carbonate, phosphate, hydroxide, amide, hydride, sulfide, oxide. This gets tricky with the strong acids. Why is it tricky with the strong acids? So for example, if I had HCl, well, what bases would HCl react with? Well, you might say HCl, would it react with bisulfate here? That's downhill, isn't it?
Doesn't have to do with, yeah.
Will HCl react with bisulfate? That appears to be downhill because we're going from a stronger acid, HCl, to a weaker acid. What would the weaker acid be? So what's happening is the HCl is donating an H to HSO4. So what we're going to form is H2SO4, sulfuric acid. So we're going from hydrochloric acid to sulfuric acid. It appears that sulfuric acid is weaker. Or is it?
Are they like the same level effect?
Yes, the same level effect. So it doesn't work here in this region. It doesn't work in this region because they're all the same level.
That'd be the same with the strong base pair.
Yep. But it would work here, you know, and so it works here and here. There's no problem, etc.
So anything stronger than nitrate? Sorry, any base stronger than nitrate?
No, any base equal to or stronger than water.
Okay.
And then we just look it up. We don't have to have it memorized. And so what we say here is any base stronger than fluoride. So another example would be that we're saying is ammonium reacts with any base stronger than ammonia. And just look it up on the chart. Another example would be HCl. Reacts with any base equal to or stronger than water. All right, let's look at this chart and see if you could figure out the pattern in reverse. Cyanide. If we pick cyanide, what acids will cyanide react with?
Anything stronger than ammonium?
I wouldn't phrase it like that. Cyanide will react with any.
Anything stronger than hydrocyanic acid?
Yes. Anything stronger than hydrocyanic acid. And so if we're looking at cyanide, cyanide will react with ammonium, because if we react with ammonium, what's going to form? What's going to form is ammonia. And if I compare it, which one's a stronger base? Cyanide's a stronger base. So we're going from a stronger base to a weaker base here.
So for the acids, you want the reversing, and for the base, you want the
Yeah, or the acids we want to go downhill. For the bases we go uphill. That's another way of remembering this. Because the bases, as you go uphill, you're really going downhill in energy. And so we can see what's happening with the acids too. When we look at the acids, we're going from ammonium to ammonia, and then cyanide to hydrocyanic acid. Hydrocyanic acid is weaker. And so likewise here, we're going from a stronger acid to a weaker acid, HCN. This is the quickest way of doing this here, but it's complicated because of the level effect, the same level effect here. Means that it doesn't work in this. There's no reaction, no driving force. All the acids are the same level here. So we're not going downhill. Does that make sense? In other words, all these acids are at the same level in water. Therefore, it's not going downhill, it's just going sideways, and we need downhill for driving force. Does that make sense? There.
So all the strong acids are going to react with any base that's stronger than water.
Yes. And so the same level means that HClO4, HI, HBr are not at the same level. That is, none are higher, none are lower. They're all the same in water. This ranking comes from what we call a gas phase. If there's no water around, then how easy is it to pluck the proton? Or it can come from theory. HCl for sure, HCl4 is the easiest to pluck the proton.
same level is determined by the gas.
No, same level is determined by water. This ranking here is determined by gas phase. And so in water, we write these all at the same level, which means when we do this downhill, uphill stuff, that they're all at the same level in trying to determine driving force. All right, so does this make a little bit of sense here? All right, we can do the exact same thing for redox. Except we don't have to worry about the leveling effect. What we do have to worry about is this. When we do acid-base, we only transfer one proton at a time. And so here, like for example, sulfate can take 2 protons because it's -2. And so we could take 2 HFs and give it 2 protons, but it would form H2SO4. What we do here is we only do 1 proton at a time. So if we do HF reacts with sulfate, it only takes 1 proton and it goes to bisulfate. It doesn't go all the way to sulfuric acid. Now we could take bisulfate and react it again with another H plus to make sulfuric acid. So we do it in 2 steps rather than 1 whole step. This is different than in metathesis. In metathesis, we react to completion. And so I'll make a little footnote here. Over here. In these are Bronsted acid-base reactions. Single protons transferred from the acid to the base. If we want to transfer two, then we'll have to do it in 2 steps per reaction. Multi-step is okay. But we have to kind of reset things and reevaluate. Do we still have driving force? Single H plus is transferred per reaction. We contrast this with metathesis. In metathesis, we transfer the max. In 1 step. So, an example of this would be like this. If I have H3PO4 reacting with NaOH, I'm going to transfer all 3 of these protons, and I'll require 3 NaOHs. This will make Na3PO4 and 3 waters. So I completely neutralize the acid. There are no more protons left on this. All 3 have been reacted or neutralized by the base sodium hydroxide. Whereas if I do this in Bronsted, I wouldn't do that. I would do this 1 step at a time. And with Bronsted, what we do is we do this. We get rid of some of the stuff. So like H3PO4 would react with hydroxide. And this would make dihydrogen phosphate, H2PO4 minus plus water. This would be step 1. If I want to neutralize the second proton, I'd do step 2. And if I want to neutralize the third proton, I'd do step 3. So we just do it 1 proton at a time. And so in Bronsted acid-base reactions, we're just transferring 1 proton from the acid to the base. All right. The next thing we're going to look at are redox reactions here. We're going to do some redox reactions in the lab. Here, let's see, I have some copper. Okay. And so we're going to take some observations today of reactions, but just for chemical properties, we're going to do this quickly, and then we'll look at this again. Over here on the right side and the left side, we have different species here. On the left side, we have the oxidizers. The oxidizers take electrons. Do you see? Fluorine's the strongest oxidizer. It's taking 2 electrons to make 2 fluorides. On the left side are the oxidizers. On the right side, we have the reducers, the conjugate reducers. And the reducers, if we were to go backwards here, so for example, fluoride is a reducer, and if we go backwards, 2 fluorides will form a fluorine and give up 2 electrons. And so the reducers we look as a reverse reaction here. The oxidizers we look as the forward reaction here. We only have one table. The table contains both. And since there's a conjugate relationship, we don't do anything. So I asked, for this particular question, I asked, what will fluorine oxidize? And so the zigzag patterns in effect here, will fluorine oxidize fluoride? Yeah, it's no, because if fluorine oxidized fluoride, what would we form? We'd form fluoride and fluorine, so there's no change. And so what we need is we need a more powerful reducer than fluoride. What's a more powerful reducer than fluoride? Yeah, anything stronger than fluoride, which in this case is anything below fluoride. So will fluorine oxidize oxygen and water?
Yes.
Yes. What will we form?
Water and
This, we are going to use the zigzag pattern here. If fluorine oxidizes oxygen and water, what are we going to form? We're going to form, well, fluorine's going to take electrons, and we're going to form fluoride and, no, not H2O. What's this called? Anybody? O3. O3 is called ozone. And H+. Is that downhill? Yes, it's downhill because we're going from a stronger oxidizer, SOA, fluorine, to a weaker oxidizer, WOA. SOA stands for oxidizing agent, or oxidizer. The weaker oxidizing agent will be ozone. So we're going, this is downhill. We're going from stronger fluorine to weaker ozone. Likewise, we're going from a stronger reducing agent, SRA, to a weaker reducing agent, WRA. The stronger reducing agent will be oxygen. The weaker one will be fluoride, because this side of the table's inverted. That's fluorine. What will chlorine oxidize? Will chlorine oxidize? If we look at chlorine, will chlorine oxidize the same stuff as fluorine? No, chlorine's a lot weaker. Do you see it's a lot weaker of an oxidizer? So it's not going to oxidize as many things. And so will chlorine oxidize oxygen? No, because that would be uphill. If chlorine oxidized oxygen, we'd form ozone. If chlorine oxidizes oxygen and we form ozone, ozone is a stronger oxidizer than chlorine. So there would be no driving force, there would be no reaction. Will chlorine oxidize iodine?
Yes.
Yes, chlorine will oxidize iodine. Because what would form? If chlorine oxidizes iodine, then we're going to form, what's this called? IO3 minus. Iodate. We'd form iodate, which is a stronger or weaker oxidizer? Weaker. And so we're going from an SOA to a WOA. This is downhill. And then likewise over here, iodine would go to chloride. If iodine goes to chloride, then chloride is a weaker RA, iodine is a stronger RA. So again, this would be downhill. Does that make sense?
Same thing as before.
Yeah, same thing as before. How about tin 2? Tin 2 is known as a great reducing agent. It's used for a lot of different things. Tin 2, what will tin 2 react with? Will tin 2 react with tin 4? No. So what do we need? Do we need something stronger than tin 4 or something weaker than tin 4?
That's a stronger oxidizer.
Yeah, we need a stronger oxidizer. And so will tin 2 react with sulfate? Actually, this is sulfuric acid. The answer is
Yes.
yes. Yeah, tin 2 will react with sulfate because what's going to happen here is we're going to form these as the product here. So the sulfate, this is actually sulfate and acid H plus is sulfuric acid. It's going to form sulfur dioxide. So if we go from tin 2 to sulfur dioxide, we're going from a stronger reducing agent to a weaker reducing agent. And this would be a driving force here. Likewise, up here we're going from sulfuric acid, sulfate and H plus, which is a stronger oxidizing agent, to tin 4. Because tin 2 is going to be converted into tin 4. And tin 4 will be a weaker oxidizing agent. And so do you see the zigzag pattern? Is it pretty? You don't really have to understand any chemistry. All you have to do is understand the pattern and then you can make the prediction. So I'm not asking why sulfuric acid is a stronger oxidizer than tin 4. We're just looking at the pattern and being able to make predictions based on the pattern. That's it.
This is redox.
This is redox.
And before we did
Acid base. So if I'm looking at the chemical properties of hydrofluoric acid, then I would look at the different things like this. If I want to put this on the chart, then I have H plus and fluoride are the components of this. HF is a weak acid, and so it just partially ionizes to these, but these are the components. So we'll look at the components of H plus. So we'll look at H plus first. What does H plus react with in the redox sense? So we go back over here and we look at H plus, which is here. H plus, what will it react with?
anything stronger than hydrogen.
Yes, anything stronger than hydrogen. So give me one.
Right.
Lead. So HF will react with lead, tin, iron, zinc, aluminum, magnesium, sodium, calcium, etc., potassium. And what happens when it reacts? When HF reacts with lead, it forms lead 2 plus. When HF reacts with tin, it forms tin 2 plus. When HF reacts with iron, it forms iron 2 plus. Do you see that? So HF is somewhat reactive. It reacts with a lot of metals. These are called the active metals. The active metals will react with acids such as HF. Mineral acids, we call them. How about fluoride? What will fluoride react with in redox? Anything stronger than what?
what's left?
Yeah, what's left? Anything stronger than what?
Fluorine.
Fluoride will react with anything stronger than fluoride?
Fluorine.
Fluorine. Fluoride will react, well, is there anything stronger than fluorine on the chart? No, so basically it's very unreactive.
Is this chart like the vaccine into?
No, this chart is not. There's stronger ones in the chart, but they just aren't listed here. So what we can say is it'll just react with any oxidizer stronger than fluorine. But there are no examples on this chart, so we can't give any examples. I could give you an example, though, of one, alpha particles. Alpha particles are stronger oxidizer than fluorine.
Can you use like the inequality signs to be easier? And just-
Yeah, sure. You could do that. So this reacts with reducers stronger than H2. An example would be lead, metal. This reacts with oxidizers stronger than fluorine. An example here would be alpha particles. Alpha particles are He with a 2+ charge. They're helium atoms with no electrons. We call these alpha particles. Alpha particles are extremely unstable, and these are formed from radioactive species. And so, finally, we look at metathesis. And for metathesis, we have H+. This reacts with bases. As in number 2. And then we have fluoride. Actually, I forgot to do fluoride in the bases part, did I? Fluoride reacts with acids. This is as in number 1. Using the zigzag. We'll just use zigzag here. Pattern. But fluoride will also react with other species. Other cations. If you remember the solubility rule, chlorides, bromides, and iodides are soluble, except for which ones? Except when paired with what cations? Calcium is soluble. Those are all soluble. I want the insoluble chlorides, bromides, and iodides.
Lead, mercury, and
One more. Nobody remembers? And silver. Silver, lead, mercury. Mercury 1, lead 2. What about fluorides? Fluorides are smaller and more reactive. than chloride. And so when we're looking for precipitates, we'll just look it up. In a reference book or Wikipedia. What? No, in general, Wikipedia is a poor source. Except for some of the scientific data, it's good. Wikipedia is just too full of opinions, you know, and people's biases, I think. And so it's not a valid source of information. Except the problem is if you want to look it up in a reference book, it costs money. If you want to look it up in the solid, like CRC or Merck, you know, which has good data, then it's going to cost you. If you want something free, then Wikipedia. And Wikipedia, the scientific information, that is the physical properties data is pretty decent from what I found. So let's see, a question that might be calcium fluoride. Is calcium fluoride soluble or insoluble? So let's take a look at calcium fluoride here. And what's pretty reliable is this, because, you know, there's very little political opinion that can get included in data like this. I mean, it doesn't matter what your beliefs are. I mean, this is just the data, and the data just should be factual evidence. There should be no particular. But the only problem with this is it up to date? Now, when you pay for the references, they make sure they have the latest, most up-to-date information, whereas this is just you know, volunteers who are trying to maintain this page. Or maybe they have some algorithms where it searches out and pulls data from the paid sources. But here we can see the solubility is 0.015 grams per liter at 18 degrees C, 0.016 grams per liter at 20 degrees C. And then we think, okay, what's our cutoff for soluble and insoluble? Does anybody remember what the cutoff is? We call things soluble if they have a solubility greater than this. We call it insoluble. 0.1. It's 0.1 moles. And so what we have to do is we have to convert 0.015 grams into moles. Well, we can do that because fluorine's 19 grams per mole. So we could just do that calculation really quick here. And so I have 19 grams per mole. I have 0.016. We'll do that one. 0.016 divided by 19 is 0.0008 moles per liter. 0.0008 moles per liter is less than, so we'd say it's insoluble. So calcium fluoride is insoluble. And it should precipitate. And so this is how we would do it for something like fluoride, which has many more. You don't want to memorize all the exceptions to fluoride because it's too many. You know, chlorides, bromides, and iodides are easy because there are only 3 exceptions: silver, lead, and mercury. But fluoride, too many to list out. All right, so that's a zigzag method. And so what we're going to do is, if you haven't finished the equations, you're going to finish those at home. What we're going to do is we're going to just take some observations today. So when we do this, if you haven't started with the observations part yet, what we do is we'll just get a test tube and just put a squirt of each in there. A squirt of this, a squirt of that, and then just observe what happens, you know, before and after the addition. Okay, what you want to do though is when we're working with some of these, you want to be careful. For example, silver ion, one of the chemical properties of silver, there are 2 things you want to worry about with silver. One, silver is a heavy metal, you know, and so it could lead to, you know, a lot of these heavy metal cations will react with proteins and stuff like that. And so you want to avoid heavy metal poisoning. And 2, silver ion is a good oxidizer. In fact, it's silver ion. What can silver ion oxidize? Let's take a look here at what silver ions can oxidize. So silver ions are here. It can oxidize a lot of stuff. In relation to the chart, it's kind of in the upper mid portion of the chart. So it's a moderate oxidizer. One of the things that could oxidize is your skin, your eyes, whatever else. If you get this in your eyes, it's bad news because the silver ion is going to oxidize your eyes. What happens? What happens is it precipitates out silver metal. When silver oxidizes something, like say, for example, hydrogen peroxide, normally hydrogen peroxide is thought of as a good oxidizer, but silver ions can oxidize hydrogen peroxide and make oxygen. But anyway, silver ions are going to make silver metal. The silver metal precipitates as tiny crystals, black crystals. In fact, you can see some of these tiny crystals here. Can you see those? It's kind of hard to see, but do you see how discolored, how black the bottom of this is? Okay, and those get into your cells. And so what happens is, it's easy to tell when somebody spills silver nitrate on their skin because it forms a black splotch. This black splotch does not wash off. You're going to have to wait until your skin sheds. This happened in Chem 4 years ago. In Chem 4 years ago, after this experiment, the student came up to me and said, I've been washing my hands for 15 minutes and the black splotches aren't coming off. And I have an important job interview coming up right after class, and I'm very worried about it. Unfortunately, there's nothing. It's not going to wash off. If you get it in your eyes, you're going to have a black splotch. I don't know if your cells in your eyes shed. Maybe they don't. But that could cause blindness, right? And so watch out for this. And usually I handle this with gloves or whatever else. So you got to be extra careful with the silver nitrate. What's that? No, you have to buy them at the supermarket or someplace. You just be extra careful. Lead, I'm not going to use the lead. Lead is also a heavy metal, but we don't need to use lead. We can use other oxidizers other than lead-2 to serve the same purpose without risking. Because I don't want anybody to spill lots of lead-2 nitrate on their hands. Yeah, heavy metal poisoning. Have to go get EDTA therapy someplace to reduce it.
What's the experiment are we doing?
5, 6, 7. You know the ones that I had numbered last time? Did you guys write down the numbers? Try to rotate this. Some people had finished this, but was it? We did reaction 1, and then what else? 3, 5, 6, 9, 7, 9. 11, 14, 16, 20, and 22. Thank you. Those are the ones we did? All right, I'm going to throw in some more for your observations. Those are the ones we did for writing out the reactions, but why don't you do these as the experiment over there. We're going to do 23, 25, 26. This is just one test tube, two test tubes here. Potassium hydroxide and sodium hydroxide react the same, so that's why I picked one of these rather than both, because they're going to give you the same observations. Uh-huh.
So what are the other questions that we have to do?
I'm sorry?
What are the other questions that we have to do? From, starting from number 11?
Other ones, just these only.
Oh, okay.
Yeah, you don't have to do any others.
Sure.
Just these ones here. And then we're going to do some single replacements for observations. And so I'll take a look at the single replacement reactions. So the ones that that weren't checked off, don't worry about those. You don't have to do those. Just skip them.
So we just do the ones assigned to us right now?
Yeah, and then for observations, we're going to do these two. I need to set it up though. We're going to do a few single replacement reactions here. So this is experiment 7. So we're going to do like C. I wrote these down last time too, right? C, which ones did I have you guys do for the reaction? C, 1 through 5?
Including 5A and B.
Okay. So here's where we're using the silver nitrate. So be careful with this stuff, the silver nitrate. The metals are located in these jars here. And so the copper metal here, we have some zinc chunks. You just need one piece of metal and a squirt or two of the solution. And the same thing with the zinc. Just one piece of zinc and a squirt or two of the solution. And then some of these are a little bit sluggish to react. And so if you don't see anything happening initially, I'll come back to it in a few minutes and see if anything changed. Uh-huh.
You have gold over there?
What's that?
You have gold?
Yeah.
No gold.
I'm sorry?
You have gold as a metal over there too?
No gold. We have fool's gold if you want some fool's gold, but no real gold.
Silver's also
I'm sorry?
Silver's also there also.
Yeah, silver would be great too, but we don't have any silver. We used to have a lot of silver in gold. And then that's silver nitrate. But the price of that stuff has skyrocketed, so it was all surplus, but now we have to purchase it, and it's quite expensive.